In the last video, we were talking about RSA and practical ways to use RSA to do encryption, in particular messages of long lengths. Messages that are much larger than you'd want to accommodate with a reasonable size modulus. When I say reasonable, of course, I'm talking about in terms of efficiency and things like that. And we looked at this scheme where you pick an element of Z star n as your per message randomness, and then you kind of, I'll put encrypt in quotes, you sort of encrypt that randomness into some value W, and that W serves as a hint on the receiver side for how to rederive the key. The key here being the hash of the underlying randomness that's hidden within W. That key then being used to key some underlying symmetric encryption scheme like counter mode. And that hint W, I use that because some people refer to this as the wrap of the key or the wrap of the secret that you need. Because, really, if you know R, then you know the key. So this is really like the secret randomness that's used for encryption. And this wrap serves as a hint on the receiver side, because if you raise that value W to the D, you recover R, and as I said, that's equivalent to recovering the key. And I said in the last video that this was an example of something called a KEM-DEM public key encryption scheme, key encapsulation mechanism, data encapsulation. And I said that more or less this first part here is encapsulating, this is key encapsulation in the sense that we're going to, this word encapsulate I don't really care that much for in this setting, but it's what people use. You're kind of encapsulating the secret randomness R within something else. It's within this string W, which is actually sent along to the receiver side, and then the data, M, is encapsulated, again, don't really care for that word, it's encapsulated within the ciphertext produced by counter mode. So we kind of walked through a little bit the proof of why this thing should work, why it is that if RSA is a good one-way permutation, that this technique actually ends up building for you an IND-CPA secure public key encryption scheme. Now, of course, with the benefit of having a domain that's as large as the underlying symmetric scheme, which is counter mode in this case. We talked through that, and in an upcoming video, I'll actually go through in some detail that proof. But before we can get to that, I need to formalize for you what is a KEM in particular. Data encapsulation mechanism is really nothing more than a symmetric encryption scheme, so you already know that piece well. What we need to do here is to formalize for you the sort of general object that is being realized by this piece on the encryption side and then this piece on the decryption side. Key encapsulation mechanism as its own object. So let's have a look at that. So here is a formalism of a key encapsulation mechanism. So as I say, it's a triple of algorithms, not unlike most public key primitives. A triple of algorithms, calligraphic K, which is going to be the key generation algorithm, NCAP, which is short for encapsulation, and DCAP, which is short for decapsulation. And associated to this triple of algorithms, this KEM is a security parameter lambda, and an associated space of keys, and we'll see why that's important in a moment. But you can think of keys as they're typically going to be strings of some fixed length, and often the string is going to be a key. The key space is going to match up with the key space of some associated symmetric encryption scheme, like we saw in the previous video where we were producing keys that were appropriate for counter mode. Typically, when you specify a KEM, when you're going to use the KEM, you're going to use it with some symmetric encryption scheme, and so this key space is going to be, it's abstract at the level of syntax, but when you instantiate it, it's going to be whatever is the set of keys for some associated symmetric scheme. So, for example, keys that are the bit strings of 128 bits long. All right, so what are these three algorithms? So I've got them here kind of in magenta highlighted. The key encapsulation, the key generation algorithm for the key encapsulation mechanism here takes in the security parameter and generates a pair of public and secret key. The public key is going to go into the encapsulation algorithm, and the secret key is going to go into the decapsulation algorithm. Key generation is clearly randomized because you have to pick, keys. The encapsulation algorithm is, again, a randomized algorithm. It takes in the public key and it returns a pair. This pair is a key K in the set of keys. So think of this key K as being like a 128-bit string. And then this associated, I've written it here as C. This is the associated encapsulation or wrap of the key K. So you can think of, I've written here as C, is because you can think of this as kind of like the ciphertext version of the key K. And this key K here is going to get used for stuff, like it's going to be used to key counter mode to do bulk encryption. And then this ciphertext of the key is going to be the thing that you actually send on the receiver side. You're going to send it to the receiver so they can decapsulate to produce this key K. And indeed, the decapsulation mechanism shown here is deterministic. It takes the secret key and it takes this ciphertext wrap of the key, and it should return for you either the key being an element of the key set, or it can return the error symbol bottom. So the correctness here looks very much like correctness for public key encryption scheme, and that is that if you, for all security parameters, if you run key generation to get a public key secret key pair, then if you run encapsulation using the public key, and notice that this is a difference from public key encryption. This looks a lot like public key encryption, except there's no actual message input. There's just a public key that goes in. But the requirement for correctness is that if you give the public key to the encap algorithm, it produces for you a K and a C. Then if you immediately were to run decap with the secret key on this key ciphertext wrap, whatever you want to call it, component C, you get back the key K with probability 1. So correctness is very much like public key encryption, and you can sort of think about this as like a public key encryption scheme. And in fact, any secure public key encryption scheme can give you a secure KEM. But there is kind of a fundamental difference here, and that is that there's no actual message. It's just you pass a public key to encapsulation, and it spits out for you a key, and it spits out a ciphertext of that key. Okay, so what does it mean? So that's the thing as a syntactic object. What does it mean to be secure? Well, it's if you remember back to the lectures on key exchange, the rough notion of security that we had there are mentioned back in that video was the key exchange literature is quite rich and broad, and there are lots of quite complicated definitions of security for key exchange mechanisms because they need to do so many things. But we had this basic notion, which was essentially that the adversary gets to observe some transcript of messages being passed, and at the end it needed to be able to distinguish the actual key produced by that key exchange protocol from a key that was uniformly random and independent of the transcript of that protocol. The definition here is reminiscent of that, in the sense that, again, we're going to basically be providing the adversary with a hint. In the case of a key exchange protocol, that was the transcript. In the case of the KEM-DEM, it's going to be the ciphertext that wraps the key. It's going to be provided this hint, and then it's going to have to decide whether or not it's actually seeing the key that is wrapped inside, or if it's being given a key that's independent of what's wrapped inside. So let's look specifically at this game. I'll zoom in a little bit here. So this is the key encapsulation experiment for key encapsulation mechanism pi, security parameter lambda, for some adversary A. It's going to be a bit guessing game. We start by flipping a challenge bit, then we run key generation to get a public key and a secret key given that security parameter, and then we pick K0 from the set of keys that the encapsulation mechanism is supposed to be producing keys from that set. We pick K0 at random, and then we actually run encapsulation with the public key to get a ciphertext wrap of the key and a key we're going to call K1. So this is the actual key that's hidden inside of this wrap ciphertext C. Then we provide the adversary, no oracles, we provide the adversary with a public key, because everybody gets the public key, and we give it the hint. We give it the ciphertext that's wrapping key K1. So this is like a hint about key K1. And then we either give it key K1, if the challenge bit is 1, or we give it this key K0 that's independent of the wrap ciphertext C. And the adversary's job is to determine which key it received. Either the thing that's inside of C or a key that's completely independent of it. And, as you expect for a key guessing game, the advantage is just twice the probability of winning that experiment of guessing the bit of the key -1 scaled as usual. Notice that there's no oracle that's provided to the adversary A. There's no oracle that's needed because encapsulation is strictly a public key input thing, anybody can compute encapsulations, right? The adversary can sit there offline and compute encapsulations all day long because it's given the public key. So it can see lots of real encapsulations. It can see keys and ciphertext wraps of those keys, as much as it likes. But at some point, it gets challenged. It gets challenged with this K sub B and the corresponding wrap of K1, and has to decide, which was it that I received. And you can kind of see how this is going to be useful, because if you imagine that you have a KEM that meets this security notion, so it meets this notion here. And what this is saying for you is, okay, if you happen to see this wrap ciphertext C on the wire, if you see this, and you can't distinguish whether or not, if I were then to show you either the actual key that's hidden inside of that encapsulation or a key that is uniform and independent of that thing, if you can't distinguish between those two, that means I could take the key that's actually inside of here, is in a sense it's completely random from your perspective, that you have no information about it. So I can actually take the key K1. Let me try this again. K1. If you can't distinguish K1 from K0 given access to C, then when the actual encapsulation is run, and I'm using K1 for something, right? The adversary is going to see this on the wire. If you think back to this RSA KEM that we had, the adversary is going to see. Of course, I've changed the names here, unfortunately, but so this is the C on the other slides. The adversary is going to see this, right? This is on the wire, and we've used the key K that is associated to this to actually produce the bulk encryption. So if upon seeing this, the key that's actually associated to it is computationally indistinguishable from an independent key, then in the analysis, I can pretend like the key that's used to create the counter mode ciphertext here is in fact just a uniform random key that's independent of everything. And that lets me then roll in the IND CPA security of counter mode, because seeing the wrap ciphertext doesn't tell you anything about the key that's being used for counter mode, so I can pretend as if counter mode is being keyed by a key that is independent of everything else, and now I can use the IND CPA security of that. So that's why this is a useful definition, because it is capturing that ability of, like, even though you see the wrap of the actual key on the wire, you can't tell whether or not, if I were to leak the key to you, you wouldn't be able to tell if it was the actual key or if it was a random key. And so then I can just act as if however I want to use this key K1, wherever I use it, I can pretend as if it is just an independent uniformly random key, because to any efficient computational test, it is a uniform independent key, even having seen the wrap of the ciphertext. So that's the KEM notion, and we can use KEMs to build public key encryption schemes when we've already built one. We just didn't actually formally call it that. I said that RSA based scheme in the previous lecture was an example of a KEM-DEM scheme. But you can build other KEM-DEM schemes. Right? You don't have to build encapsulation out of RSA. You can build encapsulation out of security assumptions that are based on cyclic groups. You can build them on elliptic curves. You can build them on all kinds of things. So that's why we lift that that one example, that RSA-based example, we lift it up to its own primitive, because it's just that important. So that's a KEM scheme, and there's an easy way to build generically from a KEM scheme and a public key encryption scheme. From a KEM scheme and a symmetric IV-based encryption scheme, there's a generic way to build a public key encryption scheme. This is just a generic version of what we saw in the previous lecture when we were using specifically RSA to build the KEM. So here's the generic construction. Let's say we have some underlying symmetric encryption scheme pi sub se, and it's an IV-based scheme, so it has an IV space. And we're going to also then say, let's say we have a KEM to go with it. And to build a public key encryption scheme now out of this KEM and the symmetric encryption scheme, we do the following. And again, this is just going to be a generalization of what we've already seen. So if this feels confusing to you, maybe you can flip back and forth between this video and the previous one to, kind of have them map to each other. So we're going to build some pi bar out of this symmetric encryption scheme and this KEM. And the way we'll do this is key generation is just going to run the KEM key generation algorithm to, given the security parameter to generate a public key and a secret key pair. And it's going to return those. Simple enough. To encrypt, we feed the public key, so to encrypt a message M under the public key. Again, I want to stress we're building a public key encryption scheme out of these two underlying primitives. We run encapsulation given the public key, and it produces for us this key wrap pair. Then we pick a nonce uniformly from the nonce space. We'll come back to this in a moment because strictly speaking, you don't need to do this, but we'll pick a nonce uniformly from the nonce space. And then we're going to run the underlying. So this is the epsilon. This is the encryption scheme from the underlying symmetric scheme. We run the symmetric encryption scheme with the nonce we just picked under the key that encapsulation returned to produce this long ciphertext component X. And then what we'll send is the wrap of the key that we used, the IV, and X. This suffices to decrypt because on the decryption side, if we call this thing here C prime, so that's this here, we get a C and a C prime. We just use the decapsulation mechanism from the KEM with the secret key on this, and just syntactically, that's going to return for us a key K. And we're going to parse C prime into the IV and the sort of long core ciphertext part, and then we decrypt under the IV using the key that we just recovered to get back the message M. This is just a very simple generic construction given a symmetric encryption scheme and a KEM of a public key encryption scheme whose message space is now whatever is the message space of the underlying symmetric scheme. And so now you have a way to do bulk encryption using a public key. So like if you have sent me your public key and I verified that it is indeed your public key, now I can just start sending you ciphertext that only you should be able to decrypt because that's the guarantee of a secure public key encryption scheme. Only the holder of the secret key should be able to decrypt. I can now start sending you ciphertexts of arbitrary length plain texts just by using this KEM-DEM approach. So I wanted to say a few more things about this construction here. Strictly speaking, we don't have to do this. Why is that the case? Well, it's the case because, as I mentioned in the previous video, we're only ever using this key once, right? We only use this key once. So in fact, any of the symmetric encryption schemes that we know, CBC mode, counter mode, whatever, doesn't matter. If you're only, remember the IND CPA notion or the IND dollar CPA notion for symmetric encryption has a key that is picked up front and then it's hidden in that oracle, and the adversary can now make lots of queries. And we have to demand that the adversary be nonce-respecting minimally, right? For counter mode, we have to demand nonce-respecting, which means you can use a counter or a random number. If you're using CBC mode, you have to use a random number as the IV. But the important point is that the key is picked once and then the adversary gets to make lots of queries. Yeah, and because it gets to make lots of queries, we needed to have per message variability, per query variability, because that key is fixed. And once you fix the key, if you had a fixed IV, then it would be trivial to distinguish whether or not the left message or the right message had been encrypted. Or in the case of ID dollar, it would be trivial to distinguish whether or not you have an actual ciphertext or a string of random bits, because you're allowed to repeat messages. And so if the IV is fixed for a fixed key, you now have a fixed mapping, right? So we needed per message variability in that setting because the key was fixed over a lot of ciphertext. But here, we only ever use the key one time. We use it one time to encrypt this message, and then the next time we need to encrypt a message, we run encapsulation again and pick a different key. So strictly speaking, we don't have to do this with any of the modes that you know of, like counter mode or CBC mode. You can just fix the IV to be all zeros. And that will suffice because you're changing the key every time you call it. You're really only calling under the key one time. So that's another thing that's quite nice actually about the KEM-DEM approach to doing things is you don't have to worry about getting the IV right. Now, so why did I say sample here uniformly from the IV space? Just in case you end up with a scheme, an underlying symmetric encryption scheme that for some reason was pathological, and for certain IVs, like maybe for the all zeros IV, it's actually bad for every key. Then you would want to avoid that, and the way you avoid it is by picking, at random from the IV space. So this is strictly speaking just a way to allow you to use any underlying symmetric encryption scheme and protect yourself against ones that may be pathologically bad in some sense. Maybe you don't know that they're pathologically bad for certain IVs, and it only comes up later on that that's the case. But for the majority of real block cipher-based symmetric encryption schemes that you're going to see, doing this is strictly speaking not necessary. You can just fix the IV to all zeros. Okay, so as I said in the RSA video, what makes this approach so nice is that while you are actually building a public key encryption scheme, you're building one where the public key operations, the stuff that's happening inside of encap, so this is going to be like running RSA or doing some sort of modular exponentiation, the expensive things are done on a very short string. So the expensive things are being done on a string that's 128 bits long, as opposed to the expensive thing being done on the plain text, which is long. All of the heavy lifting is being done by the symmetric encryption scheme. So it's really a very nice way. The first time you see it, it can either feel like cheating or it can feel quite clever. For me, it feels pretty clever, this idea that I can build the public key encryption scheme out of a symmetric scheme, and end up with a public key scheme that remains efficient even for long messages. If you know something about key exchange, I will say that we've talked about the Diffie-Hellman key exchange, which is this kind of interactive protocol where both sides contribute some randomness and there's some messages that are passed back and forth, and at the end they derive a key. If you've ever heard of something called key transport is really just doing a KEM. So key transport is like, I pick a key on my side. I have your public key. I pick a key. I somehow encrypt that key under your public key. And then I go ahead and I do the data encapsulation part. I encrypt every message I want, and then I send to you this encryption of the key that I just picked. That's key transport. And then subsequently now, when you receive that key transport piece, you can decrypt it using your secret key. You get back the key that I'm using, and now we're off to the races together. So this key transport is a way to do basically non-interactive key exchange. Assuming that I've gotten your public key already from someplace, I can immediately, with that public key, begin to send you in the first flow. So it's in some sense, it's like a zero round trip. I can send you in that first flow actual encrypted data. There's no latency in that. So if you've heard of key transport is essentially just doing what a KEM does. Yeah, if you thought about like taking this thing that we've produced here, and I first send you this, and then I send you this, I've essentially done key transport. What makes key transport different typically is that key transport mechanisms often are like full-up public key encryption schemes, as opposed to this simpler primitive KEM. What makes this a simpler primitive? Well, for one thing, a public key encryption scheme has to be secure no matter what messages are fed into it. So if you think about this, the distribution on messages is determined by the adversary in the IND-CPA notion, because the adversary is picking those messages, right? So an IND-CPA secure scheme has to be secure for all distributions on plain text messages. We're asking a lot less from the KEM, because in the KEM, we're asking it to be effectively to be secure, but only for messages whose distribution is uniform and over a set of relatively small support compared to what a public key encryption scheme would have to handle. Those messages, in particular, are going to be these keys, right? That's the thing. They're short. They're like 128 bits. They're going to be picked uniformly at random because they're going to end up being keys that are used for some underlying symmetric encryption scheme. So we are, despite the fact that the KEM looks like a public key encryption scheme, we're asking a lot less because we're only asking for security over a very pleasant, unstructured, non-adversarial kind of message distribution, in particular the uniform distribution over messages of a fixed length. So key transport will often use a full public key encryption scheme to do the work. A KEM requires less. Okay, that was an aside for people who know something about key transport. If you don't, you want to know more about it, you can go look it up. Key transport is generally speaking being deprecated for major secure channel protocols like TLS because it doesn't provide a property that we really like these days, which is called forward secrecy. And forward secrecy, although somewhat strangely named, effectively means if you are a server holding a secret key and I observe a public key ciphertext being sent to you, and then I subsequently corrupt the server and recover that secret key, now I can go back in time and I can decrypt all of those public key ciphertexts that were sent to you prior to me corrupting the server and getting the secret key. So it's looking backwards from the adversary's perspective. From the encryption scheme's perspective, it's looking forward. It's saying, if I send you this ciphertext now, it remains secure going forward, even if the secret key ultimately becomes corrupted. And key transport doesn't offer you that. KEM doesn't offer you that, right? This KEM-DEM private doesn't offer you that because if I corrupt a server and learn your long-term secret key, then of course now I can go back and I don't have to care about I can just collect up these things over time. And then if I corrupt and learn your long-term secret key, of course now I can go ahead and I can decrypt and I can get everything. So the KEM-DEM approach, key transport, they don't provide forward secrecy. And so they are, generally speaking, being deprecated. They have the upside of the fact that you get the zero round trip, non-interactive thing where we don't actually have to have an exchange. If I have your public key, I can just start sending things right away. But the trade-off for that is that I don't get this nice forward secrecy property, which people became really keenly interested in after the Snowden leaks, when it became known that nation-state intelligence agencies were doing bulk collection of ciphertexts. Even though they couldn't decrypt them now, they were doing bulk collection. And if at some point in the future they were able to corrupt and get the, whatever the master secret key for Skype or something, then they'd be able to go back into their vault and now decrypt all this stuff, right? So forward secrecy became a very interesting property for key exchange mechanisms around the time that people have been thinking about it before that, but it was really the Snowden leaks, the revelations that came from that put a big push behind building key exchange mechanisms that were forward secure. And one of the ways that you do that is you don't actually use the long-term secret key to do decryption. You create ephemeral public key secret key pairs. So it's kind of like I have my long-term public key secret key pair that I've had some certificate authority validate for us, but I only use those to create ephemeral public key secret key pairs, which are one-time use. So like for this session, I'm going to use my public key secret key pair, which is long-lived and I've paid money to the CA to have certified. I'm going to use that to generate a one-time public key secret key pair. But now, of course, we have to interact because you have to learn that one-time public key, right? So to get forward secrecy, you basically need this kind of interaction, and this is what we're seeing being rolled out in things like TLS 1.3, is this trying to minimize the amount of interaction that's demanded so that you can minimize the latency, the amount of time that's required before you can actually start sending encrypted data, but without giving up this forward secrecy property. All right. Well, so I do want to say that there is a nice generic result. So for this scheme here, we get this nice generic result down here. I'm not going to prove it in this video. Perhaps in a future video I will. But the result you get here is that the IND CPA security of the public key encryption scheme that we build here. So this is this thing here. the IND-CPA security for the constructed PKE scheme is upper bounded by twice the KEM security. This factor of 2 always shows up when we have these bit guessing games, you know that. So basically, you either break the KEM, and thereby you can distinguish the encapsulated key from a uniformly random key. If you can't break the KEM, then that means we can treat the encapsulated key as if it was an independent uniformly random one, stick it in the underlying symmetric scheme pi, and use the security property of that. So I hope at this point in the course, this kind of a bound looks intuitive. It's saying to break the PKA scheme I built, either you break the KEM or you break the underlying symmetric encryption scheme. The proof is relatively straightforward. It involves you do a reduction for the KEM part, and you show that, well, if I can't break the KEM, then I can pretend as if that key is uniform, and now I can build a separate reduction D that just uses its oracle for symmetric encryption to handle the bulk encryption part. So that is the general KEM-DEM paradigm for building public key encryption schemes that are efficient even for messages that are quite long. And in the next video, we're actually going to go back to the RSA KEM construction. Now that we have the formal definition of what a KEM is and its associated security notion, we can actually now prove formally. So we did this kind of in a hand-wavy, intuitive fashion in the previous video, but now that we have the syntax and the security notion, we can actually prove that the scheme from the previous video actually gives us a secure KEM, and a secure KEM then combined with counter mode, which is a secure IND-CPA secure encryption scheme, by this generic result gives us then that the whole RSA-based KEM-DEM construction is going to be provably a good public key encryption scheme. So that's what's coming up next.